Hey guys, my name is Shreyas and welcome to Simple Chemistry. In the previous video we did a few problems on empirical formula and molecular formula. In this video we're going to do two more problems which are a little bit more challenging and involve a little bit more thinking, but they're still pretty simple and you're going to know how to do this. If you know how to do these two problems, you're going to be very set for empirical formula and molecular formula. So let's get right into it. So, a compound contains 57.54% carbon, 33.45% hydrogen, and 39.01% fluorine. Its molar mass is 438.32 grams per mole. Determine the empirical formula and the molecular formula. So let's first go ahead and determine the empirical formula. First step is to convert all the percentages just to grams. Okay, now we have to convert all of these grams to moles, so let's get right to it. Moles of carbon is what we're looking for, and we're given 57.54 grams of carbon. And from the periodic table, we do know that 1 mole of carbon has a mass of 12.011 grams. You know, when you keep doing this, eventually you start memorizing these average atomic masses, and it starts to really stick with you. I don't want to go and jump between the periodic table and this because it's going to waste time, and you should already know how to do that, where to look on the periodic table by this point. So anyways, from here, grams of carbon cancels out with grams of carbon. We're left with moles of carbon, and then we can go ahead and do the math. 57.54 times 1 is 57.54. Divide that by 12.011. We're going to get this. Answer needs to be rounded down to 4 significant digits. Yes, so 44.791 moles. Moles of carbon. Okay, let's move to the next element. So moles of hydrogen is what we're looking for when we're given 3.45 grams of hydrogen. Okay, from the periodic table you will find out that 1 mole of hydrogen has a mass of 1.008 grams. Grams of hydrogen cancels out with grams of hydrogen. We're left with moles of hydrogen, so let's go ahead and do the math. 3.45 times 1 is 3.45 divided by 1.008. And we will get 3.42, our answer needs to be rounded down to 3 significant digits, right? So our answer will just be 3.42 moles of hydrogen. All right, and finally, let's go ahead and do fluorine, the last of these elements. So we're given 39.01 grams of fluorine. We're looking for moles of fluorine. So 39 grams, getting mixed up here, moles of fluorine, and we're given 39.41, yes, 39.01 grams of fluorine. And if you look at the periodic table, you'll see that 1 mole of fluorine has a mass of, I think it was, I already got this information somewhere, let me see, 18.998 grams. Okay, then grams of fluorine cancels out with grams of fluorine, and we're left with moles of fluorine. So from here, we can go ahead and multiply everything out. So 39.01 times 1 divided by 18.998. And we will get this. Our answer needs to be rounded down to 4 significant digits, so answer will be 2.053 moles of fluorine. Now from here, oh my goodness, moles of fluorine. Okay, so from here, let's look at the smallest number of moles. We have 4.791, we have 3.42, and we have 2.053. So we're going to take the smallest number, which is 2.053, and start dividing. So this divided by 2.053 is just 1. This divided by 2.053 is, let me see, 3.42 divided by 2.053. And this is where we're going to run into a problem. We're getting something close to 1.66. So the question is, do we round this up to 2, or do we just keep it as 1.66 and look at it as a fraction? So a general rule to go by is if you get a number which is like 2/10 away from what you're looking at, it's better to probably just round. Like let's say we got 1.82, round that down up to 2. But if you're getting a number like this, like something below that, 1.66 or 1.5 or 1.33, something like that, do not round. Keep the decimal, and I'm going to show you why later. So we can just take this as, let's say, 1.666. Here, same thing, divide this by 2.053. And that's going to equal, let's see here, 4.791 divided by 2.053. And we're getting this. And again, we're getting an answer which is which is not close to 2. It's 2.33 actually. So we're going to just take this as 2.333. Let's go ahead and do that. 2.333. Now from here, this is where it's a little bit more challenging. 2.333 is somewhere close to 2 1/3, okay? Right, 2 1/3 is 2.33333 all the way repeating. So this decimal here is very close to 2 1/3. So we're just going to take it and convert it into a mixed number like this, 2 1/3. Here, also, 1.666 is very close to 1 2/3, right? Because 1 2/3 is 1.666666 repeating. So we're going to take this as also a mixed number. And here we have 1. So from here, let's look at our numbers. 2 1/3, 1 2/3, and 1. So we can't take this and make that our formula. We can't have fractions within our empirical formula. So what we're going to do is, let me write those numbers down here. 2 1/3, 1 2/3, and 1. We're going to have to convert this to whole numbers. So the easiest way to do that, just to get rid of these 3's, is multiply all of these numbers by 3. So when we do that, we're going to get 2 1/3, which as an improper fraction is 7/3. So 7/3 times 3 is 7. Whoops, excuse me. Here, improper fraction, 1 2/3 is also 5/3. So 5/3 times 3 is 5, and 1 times 3 is 3. So these numbers here, are the numbers we're going to use for our empirical formula. So I'm going to say the empirical formula of this compound is C7 H5 and F3. This is the empirical formula. Okay? So this is an important note to take down here. That sometimes we're not going to get nice even numbers like 2.000 or 1.999. We're going to get these fractions, so we have to make sure that we don't just round because our answer will be wrong. We have to make sure that we do what we just did here, okay? That's why this is a little bit more challenging of a problem, and I included it in a separate video. So this is our empirical formula. Let's determine the molecular formula. Great. So we're already given the molar mass of the molecular formula here. Let's determine the molar mass of the empirical formula, and I'm going to use a different tab to do that. So our empirical formula is C7H5F3. F3. Okay, so we're assuming we have 1 mole of this. So 1 mole of this is going to have 7 moles of carbon, 5 moles of hydrogen, and 3 moles of fluorine. So the molar mass of carbon, or the average atomic mass of carbon is 12.011. So 1 mole of carbon is going to have a mass of 12.011 grams, and therefore 7 moles of carbon is going to be 12.011 times 7, and that's 84.077 grams. Okay. The molar. Okay, yeah. So the 1 mole of hydrogen is going to have a mass of 1.008 grams. You can figure that out on the periodic table. So 5 moles of hydrogen is going to have a mass of 1.008 times 5, which is 5.040 grams. And finally, 1 mole of fluorine, I believe I have this number here, will have a mass of 18.998 grams. So 3 moles of fluorine, we can just multiply that, 18.998 times 3, and that's the mass of 3 moles of fluorine, 56.994 grams. From here, add all these numbers together, and we will get, add all these numbers together, and we are going to get 84.077 plus 5.040 plus 56.994. We're getting 146.111. 146.111 grams per mole. From here, I'm going to take the molar mass of our molecular formula, which is 438.32 grams per mole. 438.32 grams per mole, divided by the molar mass of our empirical formula, which is 146.111 grams per mole. And we will get a number. Let's see what that is. 438.32 divided by 146.111, and we're getting 2.999, so which is very close to 3. If here you get a fraction, then that means you did something wrong, okay? This should be a whole number, very close to a whole number. So we have 3, and then from here we can take that 3 and multiply that out with our empirical formula here. So let's go ahead and do that. So 7 times 3 is 21, so we have C21. 5 times 3 is 15, so we have H15, and 3 times 3 is 9, so F9. So this is our empirical formula, and this is our molecular formula. We're done. Alright, so that took a lot of effort. Now I have a little bit more of a challenge problem here. You might see a problem like this, and these are a little bit more difficult. Sometimes you might see this as a bonus question. I remember when I was a freshman and taking pre-AP chemistry, this was a bonus question. And they are simple, but let's go ahead and look at it. You might also see this in your chemistry textbook as a problem, and I don't want you guys to be completely confused here. Okay, so these are combustion. This type of problem is called a combustion analysis problem. Okay, so we're given that. Oh, by the way, what is combustion? We talked about this a few videos back. Combustion is a hydrocarbon, which is a compound which contains only carbon and hydrogen, reacting with oxygen gas O2 to create carbon dioxide and water. It can either be a hydrocarbon reacting with oxygen, or a carbohydrate, which is carbon, hydrogen, and oxygen. Those are only 3 elements found within the compound. Okay, so the combustion of 1.50 grams of a hydrocarbon resulted in 4.40 grams of carbon dioxide and 2.70 grams of H2O. Determine the empirical formula of the hydrocarbon. The molar mass of the hydrocarbon is found to be 78 grams per mole. What is the molecular formula of the hydrocarbon? Whoa, okay, so we have 1.50 grams of a hydrocarbon reacting, okay? So from here, you have think about this. We have 1.50 grams of a hydrocarbon, and we know that the hydrocarbon is going to consist of just carbon and hydrogen. Okay, and we are getting, it's resulting in 4.40 grams of CO2 and 2.70 grams of H2O. Now, if you look at the reaction of a hydrocarbon with oxygen, let's say, for example, the reaction of methane, which is CH4. Now, this is not what the formula is for this compound. I'm just explaining this here. So CH4 plus O2 will yield CO2 plus H2O. If you quickly balance this reaction, I think you get this. 4 and yeah. So balancing is besides the point. What the important point to take from this is that all the carbon here within the hydrocarbon is going towards CO2. Okay, it's just being transferred to CO2. Okay, it's nowhere else. And all the hydrogen from the hydrocarbon is being transferred to water. So what we can do is maybe if we can find out how many moles of carbon are uh, within the carbon dioxide which is created, and then find the moles of hydrogen which are found in the water, we know that that's going to be equal to the number of moles of carbon and the number of moles of hydrogen that we started off with within our hydrocarbon. Okay, because it's a direct transfer, and we already have this information. We have the mass of the carbon dioxide and the mass of the water, so we can easily find out how much carbon is within each of these compounds, and then from there we can kind of go backwards in order to find the empirical formula. So that's the strategy here. So let's go ahead and do that. Let's see how many moles of actually let's do it with grams. Let's see how many grams of carbon are within 4.40 grams of CO2. So let me go ahead and do that. Okay, so how many grams of carbon are within 4.40 grams of CO2? Okay, so let's first convert this to moles. Okay, that's the first step. So 1 mole of CO2 is going to have, I don't want to go and work this out, I'm just going to tell you what this is here, because at this point you should be able to find out what the molar mass of any compound is. So it's going to have about 44.011 grams. So let's just take that. So 44.011 grams of CO2. Okay, so grams of CO2 will cancel out with grams of CO2. From here, we know that since the formula of CO2 is CO2, that 1 mole of CO2 is going to have 1 mole of carbon. Okay, because let's think about it. If you have 1 molecule of CO2, within that you're gonna have 1 atom of carbon. So in the same way, if you have 1 mole of CO2, you're gonna have 1 mole of carbon. And then finally, from here, we can convert this to grams. So 1 mole of carbon, you can look at this information on the periodic table, is going to have a mass of 12.011 grams of carbon. Everything's going to nicely cancel out for us. Grams of CO2 cancels out with grams of CO2. Moles of CO2 cancels out with moles of CO2. Moles of carbon cancels out with moles of carbon, and we're left with grams of carbon. Excellent. Now, let's go ahead and multiply this great mess out. So 4.40 times 1 times 1 times 12.011 divided by 44.011 times 1 times 1. Oh no, that's not what I wanted. Okay. 44.011. Oh yeah, okay. So we're getting this. Answer needs to be rounded down to 3 significant digits, so let's go ahead and we can do that. So just 1.20. Great, excellent. So this is 1.20 grams. So we know that within the CO2, 1.20 grams of carbon are created. So from here, what we can deduce is that the original hydrocarbon we started off with had 1.20 grams of carbon, okay? Because it only contains carbon and hydrogen, all right? And another thing here is that we know that the combustion of the hydrocarbon, we had 1.50 grams of the hydrocarbon, and if you just think about it, we have the hydrocarbon is only going to have hydrogen and carbon, and we already have the mass of the carbon, right? So from there, we can just subtract. If we just took 1.50 minus 1.20, we should have 0.3, let me write that down, 1.50 grams of the hydrocarbon, which is carbon and hydrogen only, minus the mass of the carbon is going to give us 0.30 grams of hydrogen. Okay, so this is what we should get. Now there's a very easy way of checking. Well, all we have to do is find out what the mass of the the hydrogen within this water here is, and hopefully that is 0.30 grams of hydrogen. So let's go ahead and check that out really quickly. So how many grams of hydrogen are in 2.70 grams of water? Okay, and this is kind of cool. Scientists actually have to do this in order to find the molar masses of different hydrocarbons. So you can be proud of yourself saying, "Oh, I am doing something that most chemists have to do." So, anyways, okay. So from here, let's convert to moles. 1 mole of H2O has a mass of 16. Let me see. Yeah, it's 18.016 grams H2O. I don't want to go ahead and take a whole nother step to do that because that's going to take so much time. And you should know how to get the molar mass of any compound at this point because we've done that so many times here. So from there, we know that from the formula that 1 mole of H2O has 2 moles of hydrogen because if you look at the same understanding, 1 molecule of H2O is going to have 2 molecules of hydrogen, so therefore scale it up, 1 mole of H2O is going to have 2 moles of hydrogen. And finally, we can convert this to grams of hydrogen. 1 mole of hydrogen has a mass of 1.008 grams of hydrogen. Okay, because this information can be found on the periodic table. Everything nicely cancels out here. Grams of water cancels out with grams of water. Moles of water cancels out with moles of water, and moles of hydrogen cancels out with moles of hydrogen. So let's see if our the information we deduced was correct. So 2.70 times 1 times 2 times 1.008. Okay, that's the top, divided by just 18.016. And yes, like we said, this is coming out to about 0.30. So we were correct there. So we have 0.30 grams of hydrogen and 1.20 grams of carbon. So this is a big step here. What our original deduction here is saying that all the carbon is going to go into the CO2 and all the hydrogen is going to go into the water was indeed correct. And we've just proved that here because now we have the mass of the carbon and the mass of the hydrogen, and when we add that together, we are getting the mass of the hydrocarbon we started off with, 1.50 grams. Excellent. So from here only can we find the molecular formula. So empirical formula. Let's first find that out first. We already know how to find the empirical formula. So what we're going to do is we have grams of both. We're going to have to convert this back to moles. Okay, so let's go ahead and do that. So moles of carbon is what we're looking for, and we have 1.20 grams of carbon. And we know from the periodic table that 1 mole of carbon is going to have a mass of 12.011 grams. Grams of carbon cancels out with grams of carbon. And when we take 1.20 divided by 12.011, we will get this. So we can just round that to 3 significant digits. So 0.0000999. 0.0999 moles of carbon. Okay, and for hydrogen, we had 0.30 grams of hydrogen, right? And we want to convert that to moles of hydrogen. And 1 mole of hydrogen has a mass of 1.008 grams of hydrogen. Okay, and then, this is grams of hydrogen. Okay, so grams of hydrogen cancels out with grams of hydrogen, and we're left with moles of hydrogen. Excellent. So from here, let's go ahead and do the math. 0.30 times 1 divided by 1.008 is this. Answer needs to be rounded down to 2 significant digits, so it is 0.30. Is that what I got here? Let me make sure. Yeah, okay. So from here, we divide by the smallest number of moles, which is definitely this. So divide this by divide this by 0.0999, and we will get 1 here, and then divide this also by 0.0999, and we should get 0.30 divided by 0.0999, and we're getting 3. Very close to 3, so 3. So from here we know that the empirical formula of a hydrocarbon is CH3. Whoa, we are not done yet. Okay, because we're looking also, the question also asks us for the molecular formula. This is a very typical like AP problem, you know, it's going to take a lot of steps. They're going to give you a little bit of points for each step, right? So it's important to go back and make sure you've answered the question completely. So we have one more part to the question. What is the molecular formula? So the molar mass of the hydrocarbon is 78 grams per mole. So let's find out what the molar mass of the empirical formula is. When we do that, you should already know how to do that. Go ahead and do that on your own. Oh no. Yeah, so go ahead and do that on your own. But what we should get is this 15.035 grams per mole. Then we can go ahead and divide what we had here, which was 78 grams per mole. So 78 grams per mole by 15.035 grams per mole. And almost there, guys. So 78 divided by 15.035. We're getting 5.2, which we can just go ahead and round down to 5. So the formula of our compound is going to be C5H15. Okay, let me just make sure that's correct. I feel like I did a mistake here. 78 divided by 15.053. Yeah, so this looks pretty accurate here. So the empirical formula is this, and our molecular formula is the C5H15. So yeah, wow, that was took a lot of effort, but that's how you do combustion analysis. So hopefully you also will get that bonus point on your test in case your teacher asks you a combustion analysis problem. But you know, that's it for now. Combustion analysis, empirical formula is as simple as that.